Hi, so let us continue by looking at some more examples. We have proved the basic convergence theorem, namely when you have a 2 pi periodic function which is Hölder continuous, then the Fourier series converges pointwise to the given function. Recall that if a function is Lipschitz continuous, then it is automatically Hölder continuous, and so our basic convergence theorem is valid for Lipschitz functions also. So now let's look at the slide. We look at the partial fractions expansions for trigonometric functions. We derive this as an application of the basic convergence theorem. So let us start with the function f of x equal to cos ax on the interval minus pi to pi. Now this function is an even function, meaning f of x equals f of minus x. It takes the same value at minus pi and plus pi. So let us take the 2 pi periodic extension of this to the entire real line. So the function does this. It takes the same value at minus pi and pi. So when you extend it as a 2 pi periodic function, what we get is a Lipschitz function. Notice that at pi and minus pi, the function is not differentiable. When you extend it, the extension is not differentiable, but the one-sided derivatives exist. They are unequal, but never mind. The function is continuous everywhere and differentiable except at minus pi and pi, but it is Hölder continuous. It's Lipschitz. So the basic convergence theorem applies. So what do? We take this function f of x equal to cos ax. We compute the Fourier coefficients a0, an and bn using the integral formulas 1.4 and 1.5. So we use these formulas 1.4, 1.5 and compute the Fourier coefficients of the function f of x equal to cos ax. So you write down the expansion, the Fourier expansion. It is valid everywhere. Now derive from this Fourier expansion the following identities. Cosecant pi a equal to 1 upon pi a plus 2a upon pi summation n from 1 to infinity minus 1 to the power n upon a squared minus n squared. That is equation 1.18 that you see in the slide. And also deduce cot pi a equals 1 upon pi a plus 2a by pi summation n from 1 to infinity 1 upon a squared minus n squared. That is equation 1.19 in the slide. Finally, if you replace a by ia in 1.19, you get equality 1.20, namely the partial fractions expansion for hyperbolic cotangent. Cot pi a equals 1 upon pi a plus 2a by pi summation n from 1 to infinity 1 upon a squared plus n squared. These are easy exercises and I am leaving it to you to work it out using the basic convergence theorem. Now we go to the next important item. We compute the Fourier transform of the Gaussian. What is the Gaussian? The Gaussian is the integral 1.21 that you see in the slide. Integral minus infinity to infinity exponential of minus x squared dx equals root pi. This is a very famous integral and I am quite positive that you have seen the computation of this somewhere in your courses. I am sure you have looked at formula 1.21 and you know the proof of this. Usually it is proved by converting this integral into a double integral. That's a classic trick. But now that you know that particular trick, let us look at a slightly different way to arrive at this formula 1.21 just for some amusement. There are numerous ways in which this integral can be computed, and it will be an excellent project for you to look at the various proofs of this important integral. And I'll give you some references for that in the slides towards the end. So here is one suggestion of the numerous ways of proving 1.21. I'm giving you one suggestion and it's a guided exercise. So now let us look at this integral 0 to infinity 1 plus x squared by n raised to the power minus n dx. Now what will happen to this as n tends to infinity? You take the limit under the integral sign. I want to compute the limit of this as n tends to infinity. Take the limit under the integral sign and you will get integral 0 to infinity limit as n tends to infinity 1 plus x squared by n raised to the power minus n. But 1 plus x squared by n raised to the power n converges to e to the power x squared. So 1 plus x squared by n raised to the power minus n will converge to e to the power minus x squared. So if you compute this integral 0 to infinity 1 plus x squared by n raised to the power minus n dx, and if you can compute it in closed form, we will get an expression involving n, and we should compute the limit of this as n tends to infinity, and we should get the wonderful number root pi. Let's see how to do this. So in this integral, it is very tempting to put x equal to square root n tan theta. If you do that, 1 plus x squared by n, what happens to 1 plus x squared by n? The n cancels out. You simply get 1 plus tan squared theta, which is secant squared theta. But luckily, we have secant squared theta to the power minus n. So it becomes cosine to the power 2n theta. And then what about the dx term? X equal to root n tan theta. So dx is root n secant squared theta d theta. So finally, the integrand becomes cos theta to the power 2n minus 2. What about the limits of integration? When x is 0, theta must be 0. When x is infinity, theta must be pi by 2. So now we have got this integral from 0 to pi by 2 cos theta to the power 2n minus 2 d theta. Everybody can calculate this integral using your reduction formula. So you get an expression. Now that expression can be identified in familiar terms. You must recall the Wallis product formula for root pi. How do you derive the Wallis product formula for root pi? Look at the next exercise. Look at the chain of inequalities. Integral 0 to pi by 2 sine to the power 2n plus 1 theta d theta is less than or equal to integral 0 to pi by 2 sine to the power 2n theta d theta, which is less than or equal to integral 0 to pi by 2 sine to the power 2n minus 1 theta d theta. Now remember, when you take an odd power of sine and integrate it from 0 to pi by 2, you get a rational number. When you get an even power of sine, when you integrate from 0 to pi by 2, you get a rational number times pi by 2. So pi by 2 gets sandwiched between two things. And now use a sandwich theorem to obtain a product representation for pi. And then compare it with what you get in the previous exercise. And you will get the magic formula 1.21. I strongly recommend you to try this out. I shall give you the solutions, not the complete solution, but the intermediate important steps. I shall give it to you later. But this is something that is highly recommended. And you get this formula 1.21. So let's see what we can do with this formula 1.21. Before we do that, in the next slide, we see some comments. A natural question is whether this formula 1.21 can be derived using complex analysis. That's a natural question that arises when you learn complex analysis. There are numerous integrals that you compute using Cauchy's theorem. So can 1.21 be computed using Cauchy's theorem? That's an interesting question. For a long time, it was believed that this integral 1.21 cannot be computed by Cauchy's method of residues. However, in 1949, Mirsky gave a very interesting evaluation via complex analysis, and that is listed as exercise number 3 on this slide. So now we got 2 more ways of computing 1.21 beyond what you know already from your undergraduate courses. Now let us see how to compute the Fourier transform of the Gaussian. Look at the slide, look at equation 1.22 on the slide. It has been elevated to the status of a theorem. It's a very important result. So what you see, the integral on the left hand side is a Fourier transform of e to the power minus ax squared. How do I calculate this integral? So let us call the integral on the left hand side I of chi. Now differentiate I of chi. So you get I prime of chi, differentiate under the integral sign, minus integral from minus infinity to infinity, differentiate cosine chi x, you are going to get minus x sine chi x. That's what you see in the middle of the slide. I prime chi equals minus integral minus infinity to infinity x e to the power minus ax squared sine chi x dx. Now the x e to the power minus ax squared turns out to be an exact derivative. It turns out to be 1 upon 2a times d dx of e to the power minus ax squared. So now you must integrate by parts. You must integrate by parts the last integral, and the derivative will shift back from e to the power minus ax squared onto the sine term. And the boundary terms will vanish because the exponential function decreases very rapidly at infinity and minus infinity. So there will be no boundary terms, and the derivative simply shifts back to the sine chi x. And when you apply it to the sine chi x, you get chi cos chi x, and the chi comes out, and you are back to the original integral that you started out with. In other words, you get a first order ODE, I prime chi plus chi upon 2a I chi equal to 0. You see that ODE on the slide. How do you integrate a first order ODE? Use the integrating factor e to the power minus chi squared by 4a. I urge you not to divide by I chi, because we do not know whether I chi is 0 or not. So avoid division by I chi, instead resort to multiplication by the integrating factor. The integrating factor is an exponential, it is never 0. That's the advantage. The process of multiplying by an exponential can always be undone because the exponential function is never 0. So take this linear ODE, I prime chi plus chi upon 2a I chi equal to 0, and multiply it by the integrating factor and solve the ODE, and you get immediately I chi equal to I of 0 e to the power minus chi squared by 4a that you see on the last displayed equation on the slide. What remains now is to compute I of 0. How do you compute I of 0? Put chi equal to 0 in the original integral. We are supposed to compute now integral minus infinity to infinity e to the power minus ax squared dx. A simple change of variables will give you the value root pi by root a, and that completes the verification of equation 1.22. So we have derived a very important result, theorem 6, on the Fourier transform of the Gaussian. Now you might wonder, why is it that I brought this up in the middle of a Fourier series discussion? We shall see now immediately. We shall derive the Jacobi theta function identity, which plays an extremely important role in number theory. So now we are looking at an application to number theory. So how does it go? Let us construct a function f of t. As you see in the slide 1.23, f of t equal to summation n from minus infinity to infinity exponential of minus t plus 2 pi n the whole squared. Now replace t by t plus 2 pi. What happens? It becomes t plus 2 pi times n plus 1. But n is going from minus infinity to plus infinity. So we immediately see that f of t plus 2 pi is the same as f of t. This function f of t that I had displayed as equation 1.23 is a 2 pi periodic function. Is it Holder continuous? It is far better than just being Holder continuous. It is differentiable any number of times. You can differentiate it infinitely often. It's a very smooth function. So it's much better than just Holder continuity. You can apply the basic convergence theorem. But what do we have to do? We have to calculate the Fourier coefficients of this 2 pi periodic function. So let's start with calculating the constant term. What is the constant term again? A naught equal to 1 upon 2 pi integral minus pi to pi ft dt. So 2 pi a naught will be equal to integral minus pi to pi ft dt. So what is integral minus pi to pi ft dt? Do a term by term integration in 1.23. Switch the summation and the integration. Summation n from minus infinity to infinity, integral from minus pi to pi, x of minus t plus 2 pi n the whole square dt. Now in that integral, put t plus 2 pi n equal to u in the integral, and what happens when t is minus pi? U becomes pi times 2n minus 1. When t is pi, the upper limit becomes pi times 2n plus 1. dt equal to du straight away. So you get 2 pi a naught equals summation n from minus infinity to infinity, integral pi times 2n minus 1 up to pi times 2n plus 1 e to the power minus u squared du. Now these integrals will simply add up to an integral from minus infinity to infinity e to the power minus u squared du. Lo and behold, we have the Gaussian and the value is root pi. So we know immediately a naught. A naught is 1 upon 2 root pi. Now let us go back to the function f. F is a even function. F is an even function because if you replace t by minus t, then it is simply exponential of minus of t minus 2 pi n the whole squared. So instead of n, it becomes minus n, and n is going from minus infinity to plus infinity. So it's an even function. Because it's an even function, the sign terms of the Fourier series drop out, namely bn is 0. All you need to do now is to calculate an. That calculation, I'm leaving it to you as an exercise. And finally, let us write down the Fourier series. F of t equal to 1 upon 2 root pi plus 1 upon root pi summation n from 1 to infinity exponential of minus n squared by 4 cos nt. So that's the Fourier series. But the basic convergence theorem tells you that the Fourier series gives you back the original function. What is the original function? Look at the last displayed equation on the left hand side. Summation n from minus infinity to infinity exponential of minus t plus 2 pi n the whole squared. And the right hand side is a displayed Fourier series. Let us try to put t equal to 0. You get a beautiful identity. Now let us generalize it somewhat. The slight generalization of this is called the Jacobi theta function identity. Theorem number 7. What have I done? It is the same as what I had done in the previous slide, except that I introduced a parameter tau. let us put in a parameter tau in the same calculation, repeat the same calculation all over again with this tau factor thrown in, and you get this theorem 7. What does it read? Summation n from minus infinity to infinity x of minus tau into t plus 2 pi n the whole squared equal to 1 upon 2 root tau pi into 1 plus twice summation n from 1 to infinity x of minus n squared upon 4 tau cos nt. Now let us put t equal to 0, and to avoid fractions put 4 tau equal to u. What do you get? Summation n from minus infinity to infinity x of minus pi squared n squared u equal to 1 upon root u pi summation n from minus infinity to infinity x of minus n squared by u. The idea is exactly the same as the previous one, namely you take this last expression in the displayed slide, f of t equal to summation from minus infinity to infinity x of minus tau into t plus 2 pi n squared. Again, that's a 2 pi periodic function. Repeat the calculations with the tau factor thrown in, get the Fourier series and apply the basic convergence theorem, and you get theorem number 7 and the special case after putting t equal to 0. So this particular thing that you get after putting t equal to 0, namely summation n from minus infinity to infinity x of minus pi squared n squared tau, has a name. It is called the theta function of Jacobi. It is denoted by theta naught of t. And what we have proved in the previous slide is basically the equation theta naught of t equal to 1 upon square root of tau theta naught of 1 upon tau. What we have proved basically is theta naught of tau equal to 1 upon root tau theta naught of 1 upon tau. The identity 1.24 is extremely important because it is very intimately related to the Riemann's functional equation for the famous Riemann zeta function. The Riemann zeta function is one of the celebrated functions in today's mathematics, and the famous functional equation is basically the same as 1.24 in a very different avatar. Let me tell you what the Riemann zeta function is, and let me tell you what the functional equation is. You see the Riemann zeta function on the slide. Zeta z equal to summation n from 1 to infinity 1 upon n to the power z. The series converges absolutely and uniformly when real part of z bigger than 1. The uniform convergence is on compact sets, mind you. Then we have the function zeta z, which is analytic in real part of z bigger than 1. Now, the series does not converge when z equal to 1 or when real part of z is less than or equal to 1. So, how do I extend the zeta function beyond the real part of z bigger than 1? When real part of z is equal to 1 and when z has an imaginary part, the convergence is extremely delicate. So, one can continue the zeta function analytically on the whole plane minus 1, and it satisfies this equation 1.25. This is called the functional equation for the zeta function. Now you might be wondering, this 1.25 is so different from 1.24. How could they be related? That is the most remarkable phenomenon. It is related via the Mellin transform. The details are available in this beautiful book by Richard Bellman on the brief introduction to the theta functions. The proof is very accessible. One can understand the argument. It's not very difficult, so I'll leave it to you to refer to this book. On page 31, you will find how 1.25 follows from 1.24. We have proved 1.24 using Fourier series, and 1.25 is just a hop, skip and jump away. And this 1.25 is one of the most important equations in modern analysis. It shows that the zeta function satisfies this functional equation. Look at the symmetry in this equation. It is symmetrical about the point z equal to half. If you replace z by 1 minus z, the left hand side goes over to the right hand side and the right hand side goes over to the left hand side. And look at the intimate connection between the zeta function and the gamma function. Unfortunately, we cannot dwell more on the zeta function because that will take us too far away from the main theme of this course. But what I want to present to you is that is the intimate connection between Fourier analysis and number theory.